Okay. So now this property actually comes into play in a very, very important way in the following aspect. Now remember, we wrote down the expression for x tilde of n. Okay, please verify from the previous page and then write down 1 over n summation k equal to 0 through n minus 1. The Fourier series coefficient, we are going to call it as x tilde of k e power j 2 pi by n k n. Okay, so basically this is the expression, or we can also write it, if you want to write it in terms of the w expression, summation k equal to 0 through n minus 1 x tilde of k w n minus k n. Okay, so basically using the definitions that we have obtained. But again, that's just for you to be familiar with that. Okay, I'm going to do the following. I'm going to take this equation 1. Okay, this is the equation for that represents the periodic signal. This is called the synthesis equation, because you are combining the sinusoids to synthesize the periodic signal. Okay, this is called the synthesis equation. So takes the synthesis equation, multiply both sides by e power minus j 2 pi by n ln. Okay, and take the summation. It's like correlation, but basically we are doing a similar operation. So what we are saying is, take a summation n equal to 0 through n minus 1 x tilde of n, that's the sequence, that's the left hand side. I multiply it by e power minus j 2 pi by n ln. Okay, so basically I'm just doing this operation. What this, you have to do the operation, same operation on the right hand side also. So on the right hand side also, this will be equal to summation n equal to 0 through n minus 1. Let's open the bracket. The term that's on the inside is 1 over n summation k equal to 0 through n minus 1 x tilde of k e power j 2 pi by n k n. That was what was inside the bracket, right? And this you have to multiply by e power minus j 2 pi by n ln. Okay. Now simplify the terms and interchange the order of summation. So interchange the order of summation n and k, interchange the order of summation, then what we get is a very interesting result, which says 1 over n summation k equal to 0 through n minus 1 x tilde of k, basically and the inner summation is over n. Anything that's not part of n I have pulled out. N equal to 0 through n minus 1, there are only two terms which are involving n. The first one is e power j 2 pi by n k n, another one is minus n. So let's combine the two of them, e power j 2 pi by n k minus ln. Okay. Now take this 1 over n inside and verify that this is nothing but the principle of orthogonality. Okay, the orthogonality property. Using the orthogonality property, we see that this is equal to 1 only when k equal to L. Okay, so then what we get is the expression that the only non-zero term is when k equal to L, or that this summation basically is 0 except if you have only one term will remain. Okay, so in basically k equal to L. Okay, only this is the term that remains. What is the left hand side? Left hand side is n equal to 0 through n minus 1 x tilde of n e power minus j 2 pi by n ln. So this is what we call as the analysis equation, which gives you the Fourier series coefficients. Analysis equation. You saw the synthesis equation at the top, and from the synthesis equation, using the principle of orthogonality, we have obtained the analysis equation. Okay, so to summarize, good idea to capture both these on a single page. Okay, so this is the synthesis equation. Okay, synthesis equation, no need the box, we can remove the box. And the next one will be the analysis equation. Analysis equation, which gives us the Fourier series coefficients. We'll just write that down. Remove the box and x tilde of L. Okay, so you have right there the synthesis equation and the analysis equation. Now it is this is basically the discrete Fourier series transform pair. Okay, so the combination of these two is the discrete Fourier series analysis and synthesis equation, and it's a very powerful result. So this is the discrete Fourier series pair. Okay, the forward transform and the inverse transform, and so it's also called the analysis equation, synthesis equation. So this is called the forward transform from the time domain going into the frequency domain, and this is the inverse transform. Okay, going from the frequency domain back to the time domain, but it's in terms of the sequences, one is called the synthesis equation, other one is called the analysis equation. Now, it is very helpful to view the discrete Fourier series as a orthogonal transformation, right? So here is the representation. So viewing the discrete Fourier series as an orthogonal transformation. Orthogonal transformation. Okay, I am sure in matrix algebra you would have studied what is a transformation. You take from one vector, you map to another vector which has got the same dimension. So that's what is called a transform. This is we're going to view this as an orthogonal transform. So here is the representation. Okay, we're going to call the Fourier series coefficients x tilde of 0, x tilde of 1, all the way to x tilde of n minus 1. These are the Fourier series coefficients. You capture them in the form of a n cross 1 vector. N rows, 1 column. Okay, so this is a n cross 1 vector. We will denote it as x tilde. Okay, that is the vector of all the Fourier series coefficients. Now, this can be written as a matrix which is n by n in dimension. Okay, the first row is all ones, and this is multiplied by the x tilde, one period of the discrete times the periodic sequence, x tilde of 1 all the way to x tilde of n minus 1. Okay, you can easily verify because x of, if you substitute L equal to 0, notice that what you will get is just a summation of all the terms. So that is the first row. The second row will now start to have the multiplication by the complex exponentials. And remember, we denoted the term w subscript n is e power minus j 2 pi by n. So instead of writing e power minus j 2 pi every time, we can write it down in the following form. The second row is given by 1 w subscript n raised to the power 1, w subscript n raised to the power 2, and the last one is w subscript n raised to the power n minus 1. So please substitute, verify that the equation that you get is the same as the analysis equation, which is, and then the next row will be wn squared, wn raised to the power 4, and the last term will be wn 2 n minus 1. Okay, if you continue in this fashion, come to the last row, this will be w subscript n raised to the power n minus 1. Second term, wn raised to the power 2 n minus 1. And the last term will be w subscript n minus 1 into n minus 1. Okay, so this is a n cross n matrix. N cross n matrix, all the entries are complex exponentials, okay, e power j 2 pi by n, and the input vector is one period of the periodic sequence and the output vector is the Fourier series coefficients. Okay, and of course this is also a n cross 1 vector. N cross 1 vector, which is denoted as x tilde. Okay, this particular vector is called x tilde, so lowercase x tilde. Okay, so now if you were to write this down in a compact form, this is how it would be. Uppercase x tilde equal to a matrix which has got dimension n cross n. We're going to call it as d of n. So this matrix we're going to call it as d subscript n times the vector x tilde. Okay, so this is the analysis equation. So we've developed a very compact representation, analysis equation. Now, how do you get the synthesis equation? Synthesis equation means you must get the expression for x. Synthesis equation. So we say that x will be equal to dn inverse times x tilde of x tilde. Okay, and by looking at the properties that we have in the expression that we have for the synthesis equation, if you go ahead and write down, you will find that this is nothing but 1 over n dn conjugate, okay, or dn Hermitian. It's a symmetric matrix, so therefore times x tilde. And so this gives us a very important result, which is helpful for us, that the synthesis equation is obtained by using the inverse of the matrix, and the inverse of the matrix doesn't have to be computed. You can obtain it just by a scale factor of 1 over n and then just conjugating the original matrix. Okay, so this is the, and because the matrix and the matrix inverse are conjugates of each other, or Hermitian of each other, this is called a orthogonal transformation. So this we refer to as an orthogonal transformation. Okay, so the discrete time Fourier series is also a orthogonal, can be viewed as an orthogonal transformation, and therefore it's got a very useful interpretation. All right. So now, of course, what we want to do is to start looking at how to apply the discrete Fourier series representation, and then also look at what are some of the properties of the discrete Fourier series. So again, let's quickly look at that. So example 1. The first example of applying the concept of discrete Fourier series. I have a sequence x of n equal to 1 for n equal to 0, and it's equal to 0 for n greater than or equal to 1, less than or equal to n minus 1. So basically it's a periodic sequence. So this is n equal to 0, then it has got a number of 0 valued samples, and then after that you will have the next period. Okay, so this is 0, 1, 2, all the way to n minus 1, then n. Similar basically, and this pattern repeats. So basically it's a periodic sequence with period equal to n, only one non-zero sample. I'm sorry? N is equal to 0. Is equal, sorry, equal to 1. Sorry, thank you. This will be equal to 1 for n equal to 0. Thank you. So if you now look at the matrix representation, what you will get is the following. You can use the matrix representation, or you can use the expression for the synthesis equation or the analysis equation. You will find that x of n equal to 1 for all values of k. Okay, so basically what it's like an impulse in the time domain giving you a constant response in the frequency domain. So again, this is not a Fourier transform, this is Fourier series. We're talking about periodic signals. We're talking about the Fourier series coefficients, and so this is the way we represent this particular periodic signal. Okay, now let's take a slightly more difficult example. Example number 2. We have a signal x tilde of n, which is given by cosine 2 pi by n r n. So basically it's the rth harmonic, and one period of that, n greater than or equal to 0, less than or equal to n minus 1. We need to find the corresponding Fourier series coefficients. So we can write this equation, this expression as 1/2 of e power j 2 pi by n r n plus e power minus j 2 pi by n r n. So basically the Euler formula we have written down. Okay, you can write it also in terms of the W expression. So this is 1/2. Okay, notice the first term will correspond to W n minus r n. Okay, make sure that you get the don't miss out the minus sign. So this will be minus Rn, and the second term will be Wn Rn. Okay, and apply the Fourier series, the analysis equation, x tilde of k. This will be equal to summation n equal to 0 through n minus 1. There is a 1/2 outside the two terms, Wn minus Rn, Wn kn, Wn kn, and the second term will be 1/2 of summation n equal to 0 through n minus 1, Wn plus Rn, Wn kn. Okay, now of course you can simplify and verify that this, from the principle of orthogonality, this will be equal to n if k equal to r. Okay, 0 otherwise. 0 otherwise. Now this term will be also equal to n, but with a different condition. Okay, if k equal to minus r, k equal to minus r. Okay. Now notice that these complex exponentials have got period equal to n. So the sinusoid with with frequency minus r can be written as n minus r. Okay, and will be 0 otherwise. Okay. So what we have is an expression where x of k is equal to n by 2 for delta of k minus r, okay, plus n by 2 delta of k plus r. Okay, so if you were to sketch this expression, maybe I can sketch it in this corner here. You will get a delta function. Let's take r equal to 3, and n equal to 8. So this is 3. You get when r, and then the other term will come when k is equal to minus r or minus 3. Minus 3. This is the same as n minus r. So n is 8, and so basically this will be equal to 5. This is your period 8, and 8 plus 3, 11 will also be there with the delta function. Okay, so you will have some zeros in between, which there's 1 0 in between here. 3, 4, 5, 6, 7, 8. Basically, you can figure out the expression that we have. Okay, 6, 7, 8. Okay, so basically, if you look at one period from 0 to 7, you will basically see this portion. Okay, you will have 2 delta functions, and each of them will be with a height of n by 2. You can also look at it from on both sides, positive and negative. So at minus 3 also there is a delta function with n by 2. So you can see that the Fourier series representation of the cosine function that we are looking at, the time domain function is actually it is one of the basis functions. So therefore, the other basis functions which are orthogonality don't contribute. All you need to do is take the basis function, scale it, and that will be the Fourier series coefficients, because your time domain signal is a basis function. Okay, I hope you are able to see that aspect. Now, important to know that just like we are now starting to get comfortable saying, okay, you give me this time domain sequence, I can obtain for you the Fourier series coefficients. You should also be able to do it in the other direction. Okay, basically apply the synthesis formula to get the expression.